Hi gang, welcome back to Geo2. This will serve as a review for the final and just sort of a synthesis of everything that we've talked about this quarter, more or less. We've talked about a lot. We've explored the Earth system kind of one piece at a time, and we'll go through that kind of quickly here. I'll do what I can to go through and add chapters to this video so that you can cut to pieces that you might not understand as well as others, and hopefully that'll make it easier for you guys to grasp the system as a whole and kind of how climate actually works. And so we start with the Earth, or really any planet. This would apply kind of universally to a planetary body that's orbiting some star. And so we have on the left here, we've got the Earth, and we're getting energy from the sun. Primarily in the visible spectrum, right? About 50% in the visible spectrum, but about 40% out in the infrared and a little bit in the UV as well. Excuse me. And so we explored this figure in some detail. At the top panel here, there's the electromagnetic spectrum with the infrared out here on the right, a little bit of visible here, and then UV, and this is the solar radiation flux coming in here. As we receive it at the Earth is the red colored in region here. And then these curves over here are the infrared radiation that's emitted back out into space by the Earth. The lines are the actual emission, but if you put a satellite in orbit, what's making it through the atmosphere is this purple shaded region here. And that's because of the absorption and re-emission of infrared radiation by greenhouse gases in the atmosphere. Okay, and that prevents a lot of that radiation from getting back out. And so we have radiation coming in here, and it's hitting the Earth at different angles, right? And so here at the equator, it's hitting at more or less 90 degrees, but out here towards the pole, it's hitting at a very oblique angle, right? And so you have differing fluxes as you move away from the equator and toward the poles. And as a result, the Earth's surface has different temperatures, right, as you move away. And because all objects in the universe emit radiation at a wavelength that is inversely proportional to their temperature, the Earth is emitting infrared radiation proportional to its temperature. And as you move away from the equator, that becomes longer and longer wavelength because it's lower and lower energy radiation. But it's all out here in the infrared, right? Okay, and so we have CO2 in the atmosphere, these little molecules there. If we kind of zoom in on those, we have these little molecules of CO2, and the infrared radiation hits them, they absorb it, and they scatter it back out in every direction, but some of that, importantly, is coming down back toward the Earth. Okay, and that leads to this pattern that we see down here in the bottom right on the PowerPoint slide, where it's absorbing and not making it out of the atmosphere. Okay, and so we have that happening basically everywhere, right? And so we have all this CO2 in the atmosphere, and the atmosphere in general is differing in temperature. Okay, and that's because of that radiation flux, right? And the differing flux of solar energy coming in. Okay, and so because we have those different temperatures, we get pressure gradients because air, like most substances, differs in its density when it changes temperature. And so colder air is higher density and therefore exerts more pressure than higher temperature air has lower density and exerts less pressure than lower temperature. Colder air is higher density. Okay, colder substances in general are higher density than their lower than their warmer counterparts. Okay, so moving on, we have pressure gradients forming in the atmosphere, right? It's warm in the subtropics, and so it's low pressure. The air is low density, and it's cold toward the poles, so it's high density, high pressure air. And so it generally flows toward the equator, or more specifically towards the intertropical convergence zone, right? Because we're spinning, however, it's subject to the Coriolis effect, and that breaks down this sort of one one convection cell in each hemisphere system into 3 convection cells in each hemisphere. So those lines there break down into these little convection cells where we have warm air rising at places like the intertropical convergence zone there, and we have cool air coming down out of the atmosphere in these divergent zones, like at 30 degrees north and south latitude. Okay. And so the atmosphere is circulating, generally speaking, like that. We can, let's see here. Turn it off here. Let me find the layer I'm looking for here. Okay, so it's kind of circulating in these convection cells. We have the Hadley cells on the north and south side of the equator, and then another convection cell in between 30 and 60 north, and another third convection cell up in the polar regions. Okay, and so those create these surface currents. If you think about how the sorry, there we go, how those lines that are closest to the Earth are moving there, right? They're coming toward the Earth from 30 degrees north and south, and then away from 30 north and south towards 60, where there's this other convergence zone. Okay, and so we have those convection cells moving and creating these flows on the Earth's surface, but because of the Coriolis effect, objects in the north are deflected to the right, and objects in the south appear to be deflected to the left. And so those straight lines turn into these curved lines here. And that gives rise to the dominant winds that we experience on the Earth's surface. We have the trade winds north and south of the equator that flow from east to west, really more specifically southeast to northwest and northeast to southwest. And then we have the westerlies up near 40, 50 degrees north and south that are flowing from west to east. Okay, and so we take those arrows off. That's kind of the picture of the globe that we've created so far. We have these convection cells that are circulating at altitude, right up here. Oh, let's see here. We have these convection cells that are circulating here at altitude, right? And those are giving rise to these winds that are flowing across Earth's surface, right? Okay, so we've built that picture so far. Now that is, atmospheric circulation at the surface. The temperature of the atmosphere differs, right? We know that it gets colder as you move higher in altitude, and we also know that warmer air holds more moisture than colder air. And so as warm air rises in altitude, it cools off and it loses its moisture, it precipitates, right? It rains. And so if you remember back to those satellite images that we looked at, there's clouds at the intertropical convergence zone where there's warm air rising, warm, moist air rising up in altitude, getting cooler, and its ability to hold moisture drops, and so it begins to rain. Okay, and so we have lots of rain here at the intertropical convergence zone. Similarly, we have rain up here at these convergence zones at around 60 degrees north and south. Okay. Excuse me. All right, so that gives us an idea of where we can expect precipitation. And similarly, at 30 degrees north and south, there's cool, dry air that's coming from high up in the atmosphere, high altitude. It's getting so cold and so dense that it begins to sink back down toward the Earth's surface. And as a result, we're getting lots of, it's warming up as it's coming down, and its ability to hold moisture is increasing, and so it's soaking up moisture. It's driving evaporation, right? There's not a lot of precipitation occurring at 30 degrees north and south, right? Okay, and so we have these winds that are driving these dominant wind patterns, the trade winds and the westerlies. And that wind is blowing continuously across Earth's surface. And so that wind exerts a force on on water that it's blowing across. Let me see where this layer is here. And so if we were to draw some continents on here, like I have here, you see that the air is blowing across continents, but it's also blowing across water, right, across the oceans. And so that sets water into motion. And if we look at the Atlantic Ocean like we are here, the trade winds are going to create these equatorial currents that are flowing, generally speaking, from east to west across the ocean basin, the Atlantic here, in the North and South Atlantic, just north of the equator, just south of the equator, right, flowing from east to west. Right? And they're generally speaking warm water because they're in equatorial latitudes, right? They're getting lots of solar radiation, and they're absorbing that and they're warming up. Right, when they run into continents, they tend to bend, respectively, to the right or left, whether they're in the northern or southern hemisphere, and that gives rise to these western boundary currents. They're warm water currents, like the Gulf Stream and the North Atlantic, similar ones in other ocean basins. Right. So, if we look at the Pacific instead of the Atlantic, let's see, where are we here? Get rid of those for a second. Oops. These are the ones I want to get rid of. Let's see. There it is. Okay. If we look at the Pacific, we get a very similar pattern of circulation. You have the equatorial currents, northern equatorial current and southern equatorial current, flowing from east to west across, and they create, in general, these gyres, these circulation patterns that flow like this in the North and South Pacific. All right. So if we think about this kind of in a broader context now, we have this really quite coupled ocean atmosphere system where we have energy coming from the sun, and the flux is different based on latitude. It creates different temperatures that drive circulation by creating pressure gradients in the atmosphere. Warmer air exerts less pressure, less force than colder air because it's lower density, right? And so we have these trade winds and westerlies that kind of result from that process, coupled with the fact that we're on a rotating sphere. We have convection occurring in the atmosphere because of that. Okay, and because of that convection and that where that convection occurs, we have precipitation distributed in specific regions of the globe, right? More specifically, in subtropical latitudes and around 60 degrees north and south, plus or minus. Okay, and so we've now got this picture, and we have the ocean circulating like this, and we can expect to see precipitation in specific regions and deserts in other regions, right? And so this is sort of the conceptual model that we've built so far, and we're doing pretty well. We have the Sahara, right? We've got the Sahara Desert. We have the Congo and the Amazon in the right places, roughly. There's lots of desert up here. The Arabian Peninsula, the Gobi Desert. India looks pretty forested. It's tough to draw things at the right latitude, right at the edge of the globe. But in general, we're doing pretty well here. We've recreated most of the dominant climatic features that we see, right? And you might be wondering, well, over here, the east coast of the Americas isn't desert. Well, that's primarily because we have this warm water current that flows up through the Caribbean and up along the eastern seaboard, the Gulf Stream. And so there's lots of warm water at the surface driving evaporation and subsequently precipitation in that region. But if you follow that latitude across, you get into the desert Southwest, right? And where we live in Southern California, which is a desert, certainly where we live here in Riverside. Okay, so that is kind of where the climate stands as an instantaneous entity, right? The energy, the amount of energy that exists in the system is a function of how much radiation we get from the sun and how much radiation we allow to go back out into space. Really more specifically, how fast we allow that radiation to go back out into space, right? And so we had this figure that we saw, this slide that we saw, where it's just like this reservoir here where water's flowing in and water's flowing out. Energy is flowing in and energy is flowing out, and it's at steady state, assuming that temperature isn't changing. Global average surface temperature, that is. And CO2 is in here acting like a little valve, that the more CO2 is in the atmosphere, the more infrared radiation gets re-emitted toward Earth. And so it takes longer for the radiation, or the energy more specifically, to get out of the system. And so that dictates the average global surface temperature. Now, because we're spinning, and how fast we're spinning, really more specifically, we have a certain number of convection cells in our atmosphere. And those convection cells are operating because of the unequal distribution of solar radiation on the Earth's surface, because it's curved, right? So the flux isn't equal everywhere. And so it drives pressure gradients, that drives circulation, that creates distribution of precipitation that exists, and it also drives ocean circulation, because it creates the trade winds and the westerlies, which really create the gyres that we see in every ocean basin. Okay, so now we want to take that a step further and think about how that changes through time, and how certain aspects of the system affect one another and could lead to increases or decreases in temperature. And we want to explore how that will affect the system as a whole. Okay, and so we go from here. We kind of we've identified carbon dioxide at this point as a key player in this whole game, right? It's a key constituent of the atmosphere, of the greenhouse effect, right? If we go back to that for a moment, water vapor contributes an enormous amount of the greenhouse effect. However, the amount of water vapor in the atmosphere is a direct function of the temperature. Warmer air holds more moisture, and air will drive evaporation if moisture is present, right? And so that will vary as a function of temperature directly. Carbon dioxide does not directly vary as a function of temperature. We've explored a lot of feedbacks. When you raise or lower global temperature, it affects carbon dioxide, but not directly, not the same way that it does water vapor. Okay, and so carbon is really important here. All right, and so we're going to, from here, we're going to explore how changing carbon dioxide levels can affect, can be achieved, essentially, right? Okay, so back to our globe here. If we get rid of these continents and everything for a moment here, we'll keep the atmosphere circulating. Let's get rid of the trade winds, get rid of the ocean circulation. Where are the continents? Oh, goodness. Where are they? There they are. Okay. All right. So we went from there to talking about other places in the Earth system where convection occurs, right? First, we sort of laid out how the Earth is structured, the Earth's interior, right? We said that there's a mantle beneath the crust, and then beneath that mantle there's a core. We said that the core experiences convection. Let's get rid of these for a moment. The core experiences convection, right? In the outer core, there's an inner core that is solid nickel iron, and there's an outer core that is liquid. And that liquid outer core experiences convection. And because it does, we have a magnetic field, right? That comes in into the north and out of the south in these kind of magnetic field lines, like we talked about, and they intersect the surface at these differing angles, right? Maybe if we change this to, I guess you can kind of see those little arrows there. We could change the background color. There you go. You can see them there. The little arrows there, and they intersect their surface at differing angles, right? And so we have a little compass here that is pointing north, as compasses do, and that's the declination of the compass. They point north. However, they also have an inclination, that compass needle, and that responds to how far away from the North Pole you are, effectively, or what your latitude is, right? How that intersects the Earth's surface. Right, we talked about how that's used to reconstruct the movement of tectonic plates, and more specifically continents, throughout Earth's history. Okay, let's go. Just turn that off for a moment. Okay, so we have our little planet here, floating in space now, appropriately, and it has a magnetic field because we have a liquid outer core which is experiencing convection. There's also convection going on in the mantle, right? In that uppermost layer of the mantle known as the asthenosphere. Okay, there's also convection. There's a lot of heat being generated through radioactive decay, primarily, inside of Earth's interior. And that heat wants to get out because outer space is cold. And so just like if you put a metal rod, you put one end of a metal rod into a fire, it's gonna get hot all the way up the metal rod. Heat wants to equalize in a system if things are in exchange. And so the Earth wants to get that heat out, and the heat's being generated from inside. And so it warms material, and that material becomes lower density, and it rises if it's able to, right? And so the uppermost mantle is in a state where that's possible. And so we get convection in the asthenosphere. Okay, and so I've drawn in here, little convection cells, red warm material rising, flowing towards to these convergence zones and rising, and then cooling off as it rises and turns into blue arrows, and the blue arrows flow laterally out and then converge again at the further further toward the surface, and they sink because they've lowered enough in temperature by that time and they become high enough density. Okay, they sink and then they spread back out. Okay, and so that really the traction that exerts on the crust, which is sort of this blue stuff in this diagram, creates plate tectonics, or largely contributes to driving plate tectonics. Okay, and so we have plates on the crust is made up of individual plates, and at the boundaries of those plates, different things can occur, and so that's really shown here. We have different crust on the planet. We have continental crust and we have oceanic crust, and they differ fundamentally in their properties. Their chemistry is different, and because their chemistry is different, their densities are different. Oceanic crust is much higher density than continental crust. The mineral makeup of them is very different, and it has lots of consequences. But one of those consequences is that continental crust doesn't readily subduct. Oceanic crust does subduct, and so here we have a convergence zone, if you will, in the mantle. We have hot material coming in from both sides, right, and then it rises, and at that zone where hot material is rising, we have volcanism, a mid-ocean ridge in this case. We could go ahead and add some oceans in here. Excuse me. And so we've got hot material rising. Let's see. Let's get rid of those little guys. We can put our oceans back. Okay. So we have hot material rising, creating these divergent plate boundaries, mid-ocean ridges. or rifts if they're through continent, but rifts in time will turn into new ocean basins and new mid-ocean ridges. And so the East African Rift, for example, the Horn of Africa, Somalia, and sort of Eritrea, I think, is on that side. At least part of it will kind of tear off the side of Africa, and a new ocean basin will develop there. But in any case, so these divergent boundaries are generally speaking mid-ocean ridges. And so as you see here, new crust is being created at the ridge, and it's spreading outward from the ridge in both directions. We have a continent over here on the right-hand side of this. Now, right here, we have a continent. It has what we call passive margins on both sides of it. There's no subduction occurring. The plate is continuous from the continental crust over to the oceanic crust. Can't do that right now. So they're passive margins, right? And that differs fundamentally from, let's see, here's a continental margin that's characterized as an active margin. We have subduction taking place beneath the continental crust. Oceanic crust is being forced back into Earth's interior. And when that happens, heat and pressure causes volatilization of certain things, melting of certain things, dewatering. All of those factors contribute to volcanism. And so these subduction zones are characterized by lots of earthquakes and lots of volcanism, right? And so the Andes Mountains are a great example in South America of subduction-related volcanism, a mountain chain on a continent that's created by that. You can also have, like we have here, let's see, right there, you can have subduction of ocean crust beneath other ocean crust, which generally results in an island arc, something like Indonesia or Japan. You have large earthquakes like we see in Indonesia and Japan, and you have volcanoes like we see in both, right, creating this chain of islands that runs parallel to the subduction zone. Okay, so we have this plate tectonic view. Let's get the whole Earth there back. So we have plate tectonics on the Earth, right? And that's really important. It's important for a whole bunch of reasons that we talked about, but at this point in this review, let's just say it exists. All right, and so we're now kind of here. We have continents and oceans, and we're on a planet which has, let's see here, where's a good one of these? It has an atmosphere, right? It's radiating infrared radiation, and that's driving circulation in this atmosphere because it absorbs that infrared radiation, and it circulates, right? And so we have rain in certain spots on this planet, and we have certain climates in regions in response to that. And so on this hypothetical little planet here, we would have rain here, and so we might have, we're approaching 60 degrees north there, so that northernmost landmass would probably be glaciated if we were in a glacial episode, but we would have some forests there, probably like temperate rainforests. Down here, we at the equator, right? That's the equator. Down there, we would have rainforests. Here on this continent, we would have a desert, right? And so we've kind of recreated the climate here, and the distribution of continents, and that's really important for a variety of reasons. Primarily because as we move further with the discussion of how climate varies through time, what we're gonna have to talk about is how carbon is cycled through the atmosphere and other relevant reservoirs that exist on the planet that interact with the atmosphere, right? And so that sort of takes us into the realm of chemistry specifically. And so we can kind of zoom in, on one one continental margin here, and we can talk about the relevant reservoirs of carbon dioxide and how carbon, or the relevant reservoirs of carbon on the surface and how they're cycled. We could zoom in on a passive margin like this one. We could zoom in on an active margin. Wherever we have one, there's an active margin there. We could zoom in there and look at that margin, talk about how carbon is cycled there. But in general, that's going to take us to a new picture here. Okay, so we have a continental margin, and we're interested in how carbon is being cycled, right? And so we broke carbon up into organic carbon and inorganic carbon. We said that they are sort of distinct from one another, specifically in their redox state. Inorganic carbon is oxidized carbon, and organic carbon is reduced carbon. Okay, and so that means they make up different classes of molecules. Organic carbon is primarily built through biological processes, though it can be produced abiotically, but it's primarily produced through biological processes, right? And so we talked about the short-term carbon cycle is photosynthesis and respiration, effectively, right? And photosynthesis takes atmospheric carbon and it turns it into organic matter. Life makes all kinds of complicated molecules out of that. And then respiration takes that organic carbon and it breaks it back down into CO2, oxidizes it more specifically into CO2, and it gives off energy. The organism gains energy by doing that. Okay, that sort of makes up the short-term carbon cycle. There's also the long-term carbon cycle, right? And the long-term carbon cycle is kind of made up of the inorganic side of things, and so we have water evaporating from the ocean, right, into the atmosphere, and it's condensing and forming rain. That rain, excuse me, that rain combines with carbon dioxide in the atmosphere to form carbonic acid. We talked in a little bit more detail about carbonate equilibrium and how carbon dioxide actually dissolves into water and what happens as a result. It actually speciates into carbonic acid, bicarbonate, and carbonate, and the relative ratios of those three to one another varies as a function of pH. Regardless of the specifics, when you dissolve CO2 into water, it creates acidity, and that acidity dissolves rocks. Okay, and so we have acidity, we have the silicate weathering reaction down here in the bottom left, where carbonic acid reacts with a silicate mineral to liberate calcium in this case and create bicarbonate. Those are delivered to the oceans by streams and rivers, right? And through that process, we'll say streams deliver calcium and bicarbonate to the ocean, where it accumulates, and it can react. Those two ions can react with one another, calcium and bicarbonate, and they can form calcium carbonate, which precipitates and forms carbonate rocks. Okay, so calcium plus bicarbonate forms calcium carbonate, and it precipitates into a rock which can survive for millions or even billions of years, right? And so through this process, we have taken carbon dioxide out of the atmosphere, and we have turned it into a rock. We take CO2 out of the atmosphere, turn it into carbonic acid here, react that with some rock, delivering bicarbonate and calcium to the oceans, where they react to form limestone, calcium carbonate sediments. Okay, that can stay stable for a long time until it's subducted or perhaps uplifted and eroded, but destroyed in some way, in which case most likely that material is going to be re-oxidized either through metamorphism or through volcanism, and re-released to the atmosphere as CO2. And so that completes our long-term carbon cycle here. Carbon dioxide is being released from volcanoes. It's being absorbed or solvated by water, falling rain in the atmosphere, turned into carbonic acid, where it reacts with rocks, forming bicarbonate, which turns into calcium carbonate. Okay, that is the long-term carbon cycle. Right. We also have a short-term carbon cycle here, right? Let's see. Let's see here. I have a better picture of the short-term carbon cycle. This one, I like this one a lot. So we have this situation that we talked a lot about in the ocean, and this would be, in any aqueous environment that's deep enough. You have a situation where you have, first of all, we have sunlight coming down, and it doesn't get all the way to the bottom of the ocean, right? So you have darkness below some certain depth, and you have no photosynthesis in that dark area, right? And so also, not only is there no photosynthesis down there, but because you have darkness, because you have sunlight hitting the upper water column, it warms up, and warm water is lower density than cold water, just like warm air is lower density than cold air. And so you have this strong temperature gradient, right, that exists in the ocean. Low density warm air, water at the surface, and high density cold water at depth. Not only is there a temperature gradient, there's also a salinity gradient, right? Deep water is more saline, higher, it has more salt dissolved in it than surface water. And the combination of those two factors creates this density contrast, where you have low density surface water sitting on top of higher density deep water, and that's a stable stratification, is what we'd say. It's stably stratified. The two will tend not to mix with one another unless they're really forced to, or that density contrast is lessened somehow, right? And we talked about how that can actually occur, and deep water can form by lowering temperature at high latitude in the surface water, and also by increasing salinity through the formation of sea ice, right? And that breaks down this density contrast, the pycnocline, as we said, we called it, breaks down the pycnocline, and as a result, water can move kind of freely up and down in the water column. You can also force deep water up to the surface through upwelling in zones where water is moving offshore, perhaps because of Ekman transport. Okay, so you have this density contrast in the water column, and only the upper water column is getting light, and so you have lots and lots of photosynthesis taking place in the upper water column. You also have lots of respiration. In the lower water column, you only really have respiration, right? And so I don't think, unfortunately, that I drew the actual chemical equations on there. Well, I suppose I have them here. Okay, perfect. Very good. Let's stay with this picture. Okay, so the short-term carbon cycle, right? We have photosynthesis and respiration. Oh my goodness, I don't actually have them here. I do have them here. Let's grab a different. Okay. There we go. Okay, so photosynthesis is taking carbon dioxide and water out of the environment, and it's turning it into organic material and oxygen. And respiration down here is taking organic material out of the environment and oxygen and turning it back into CO2, right? You're getting energy out of respiration, and you're fixing carbon using energy from sunlight here. Okay, and so everybody in the environment is doing respiration to gain energy to carry out cellular processes, and they're doing it using organic carbon that was fixed through photosynthesis. All right, and so up here on the left, on our little idealized margin, our little cartoon here, we have lots of photosynthesis in the surface ocean, and we have lots of respiration also in the surface ocean. Carbon is constantly being cycled. However, a small fraction of that is settling downward, right? And so we gave that a name. It's called the biological pump, and it's constantly taking organic material that contains carbon and also, maybe more importantly, nutrients, and it's exporting it from the surface ocean to the deep ocean. We call it export production. It makes up maybe 1% of total primary productivity. 99% is respired in the photic zone. About 1% sinks down. Now, below the photic zone, there's still respiration taking place, right? And so respiration is still taking organic material and oxygen and turning it into CO2 and water and releasing anything else that's in there, like nutrients, right? Importantly. Okay, and so if you look at total photosynthesis, right, it's here, it's really high in the surface ocean, and then it drops to nothing in the deep ocean as soon as light is no longer present. But respiration doesn't. It's pretty high in the surface ocean, but it takes a while to decline in the deep ocean, and that's because as you move lower, less and less organic material has survived all that respiration, but there's definitely a lot of respiration going on down there. Okay. So, as a consequence, right, you get this nutrient profile in the ocean that looks like this. Nutrients are being quantitatively utilized in the surface ocean. They're being taken up constantly and incorporated into biomass through photosynthesis. But in the deep ocean, all that biomass is being broken down and the nutrients are being re-released to the environment. And so down at depth, nutrients are being released into the water. They're being consumed in the surface ocean, exported to the deep ocean, and then released. And so as a consequence, you have very low nutrients in the surface ocean. And as you get below the photic zone here, the nutrient profile, don't show that later. As you get below the photic zone, the nutrient levels spike, where you're in the zone of rapid respiration or high respiration. Okay. So all that respiration consumes a lot of oxygen. And so as a result, you can have the formation of these oxygen minimum zones that we talked about. Quite frequently, below productive margins, you have the formation of an oxygen minimum zone. Oxygen can go all the way to 0, potentially, at some depth. And they usually form these kind of wedge-shaped zones, zones off the coast of upwelling zones, primarily. This is important for a variety of reasons, but it helps in the preservation of organic carbon. And so, why we're really talking about all of this is because some amount, maybe 0.01% of total primary productivity that's occurring in the photic zone up in the surface ocean actually makes it to the sediments, and it's buried along with the carbonate carbon and all of the other sedimentary material that's being deposited on the seafloor or on the continental shelf, and then over time becoming a rock, becoming lithified into a rock. And so that link, right, between the biosphere or biomass and sedimentary rocks, organic matter burial here in the middle, that's a really, really important sink for carbon dioxide. Sink means that's where it takes it out. It's a really important export for atmospheric carbon dioxide. If you can fix atmospheric carbon dioxide into organic matter through photosynthesis, right, and then bury that organic matter in the sedimentary rock reservoir through organic matter burial, then you have it locked away for millions to potentially billions of years, right? And so we looked at these different carbon reservoirs that exist on the planet, and we have by far the two major reservoirs are carbonate rocks, about 40 million gigatons of carbon, and organic carbon in sedimentary rocks, about 10 million gigatons. So about 20% of the total sedimentary carbon reservoir is organic carbon, about 1/5. Okay, so we've talked about photosynthesis and respiration, how the short-term carbon cycle here just kind of spins and spins and spins on yearly, really seasonal timescales down to daily timescales. And then we have chemical weathering and volcanism, the long-term carbon cycle, which is taking CO2 out of the atmosphere, making carbonic acid, reacting with rocks, forming calcium and bicarbonate, which combine to form limestone and are preserved as sedimentary rock. Those can be weathered, they can be metamorphosed, they can be subducted and volatilized and returned to the atmosphere through any one of those processes as CO2. Okay, so with that, I think that more or less covers what I wanted to look at here. So from there, we went on to talk about short-term and long-term climate, and so now in this review, the last 45 minutes, we've gone through how energy comes in from the sun and is received by the Earth, how it's re-emitted by the Earth's surface, how the atmosphere absorbs that infrared radiation and re-emits it back, creating a warmer climate than we would have without the greenhouse effect. We identified carbon as the key component of the atmosphere that controls that. And we talked about how that drives atmospheric and oceanic circulation. We also talked about plate tectonics, how that recycles things and uplifts new rock. And we talked about how that new rock that's exposed is subject to chemical weathering because rain and carbon dioxide combine to form carbonic acid. And so through that chemical weathering and also through organic matter burial and or organic matter uplift and weathering, oxidation by the atmosphere, you can modulate CO2. We have two different inputs and outputs, right? So again, if we're at steady state, right, the input equals the output. That is steady state. And so if the temperature on the Earth's surface is at steady state, then we have some amount of CO2 in the atmosphere. Now, there are basically two cycles, two separate inputs and outputs that are occurring. We have chemical weathering and volcanism. That's the long-term carbon cycle. And then we have photosynthesis and respiration. That's the short-term carbon cycle. So we have respiration and volcanism, two different faucets or pumps coming into the reservoir. And then we have chemical weathering and photosynthesis, these two different valves that are letting CO2 out of the reservoir, right? And so we can change any one of those and it will change the relative amounts of carbon in these different reservoirs. And so we explored a whole bunch of different feedbacks that exist on the Earth's surface. Over longer time scales, we talked about processes like supercontinent formation and breakup and how that can either increase or decrease chemical weathering by uplifting large mountain ranges. It can increase organic matter burial by increasing photosynthetic production, delivering nutrients to the ocean because of the weathering of continents, because nutrients are needed, right? And they're limiting productivity in any sunlit environment. So if we uplift mountains, the rocks that are exposed weather chemically and they provide nutrients as well as calcium and bicarbonate, right, to the oceans. So they stimulate productivity. And so by uplifting a large mountain range, we're enhancing chemical weathering, we're enhancing photosynthesis. Those are the two valves taking carbon dioxide out of the atmosphere. And so if we enhance both of those, then the amount of carbon dioxide in the atmosphere goes down, shrinks, that reservoir shrinks, right? Similarly, if we somehow enhance respiration or enhance volcanism, maybe we break up a supercontinent and we drive lots of volcanism without somehow correspondingly increasing chemical weathering, then we can increase CO2. If we increase respiration without correspondingly increasing photosynthesis, we'll drive an increase in atmospheric CO2. We're doing that right now artificially, right? We're taking oil and gas out of the ground. Oil and gas are nothing more than organic sedimentary carbon. Okay, it's just organic carbon, like any biomass that's survived some amount of time and made it into the sedimentary rock record. When you expose that biomass to heat and pressure, a variety of things happen, but it gets transformed into saturated hydrocarbons, oil and gas. And so what we're doing, oxidation or combustion, is just an oxidation reaction, right? It's the exact same as respiration. Just like you gain energy by respiring, by breathing in oxygen and eating a cheeseburger and then combining the cheeseburger with oxygen, you gain energy by oxidizing gasoline or natural gas, right? Methane. You gain energy, lots of it. And so, but it's the exact same. And so what we're doing today is we're basically, we're doing sort of accelerated, we're doing an alternative to respiration. We're combusting or oxidizing organic carbon that has been stored in the sedimentary rock record for a long time. It used to be CO2, it was buried, and we're extracting it sort of artificially, right? We're not letting plate tectonics uplift that organic carbon and expose it to the atmosphere and allowing it to weather slowly. We're accelerating that process. And so we're accelerating respiration without correspondingly increasing photosynthesis. And so atmospheric CO2 is going up. It's just a direct cause and effect. And so we talked about, how you can, right? We started with system science and talking about just feedbacks and steady state in conceptual terms, right? But we started with that concept because that's what we end with, right? You can drive changes in a reservoir by changing the inputs or changing the outputs. It's a very complex system that we're dealing with here. It has many moving parts, right? Many individual components. And when you change one component, you oftentimes affect many of the other components. And so we talked a lot about feedbacks. We talked about how increasing ice cover reflects more sunlight, the albedo feedback. It's a positive feedback. We talked about how increasing temperature will increase chemical weathering, the silicate weathering feedback. It's the most important feedback in the system. By increasing global temperature, you increase rain because you increase the amount of water in the atmosphere, and you increase the rate at which the chemical weathering reaction takes place. This reaction here, carbonic acid plus a silicate rock creates bicarbonate and calcium. That reaction occurs faster when temperatures are higher. Most chemical reactions take place faster at higher temperatures. And so you have the actual reaction itself taking place faster, and you have more places for the reaction to take place because you're creating more rain by evaporating more water in the atmosphere and then precipitating more. So you have more places for the reaction to take place, and the reaction is taking place faster. So chemical weathering accelerates when temperatures go up. And chemical weathering at the end of the day here takes CO2 out of the atmosphere and it turns it into rock. And so if you accelerate this process that takes carbon dioxide out of the atmosphere and turns it into a rock, then you're lowering CO2, and as a result, you're lowering temperature, right? And then this process will slow down. And when this process slows down, then CO2 in the atmosphere will increase. Temperature will go up, the process, chemical weathering, will speed up. So it's a negative feedback, and it's a really powerful negative feedback. And it's really what we believe has, or what science tells us, rather, what science tells us has kept our planet habitable for the past 4.5 billion years. It's kept global surface temperatures so that we have liquid water at the surface for the entirety of our history, and that's super, super important. So that's sort of where we left the discussion. There were obviously maybe 6 or 8 other feedbacks in the carbon cycle that we talked about. Feedbacks, more general feedbacks that aren't specifically related to carbon also, but related to temperature, like the albedo feedback, for instance. We talked about quite a few of those. So I would, encourage you obviously to understand those and be comfortable with them. After that, this last lecture that we had was just on climatic records and how we understand the past climate, how we reconstruct the past climate, and why the record looks the way that it does. And so we really, in that, it's called lecture 9, we really tackled two concepts. Here, let me just bring up lecture 9. I don't have it opened. Lecture 9. So, lecture 9, there it is. Okay. Was this long and short-term climate. We started off talking about how the Earth hasn't actually been in a glacial episode, or in a glacial climate for very much of its history. Let's see if I can get that size better. No, that's not really. It's actually been in a greenhouse climate for most of its history, and especially during this Phanerozoic time period. We talked about the conditions that are required to create glaciation, that it obviously requires low carbon dioxide, so the greenhouse effect isn't creating warm surface temperatures, or too warm, but it also requires high latitude continents and specific ocean circulation patterns. This is the record of CO2. It's reconstructed from a variety of different proxies. There's nothing we can go into a 400 million year old rock and measure CO2 directly, but there are a variety of geochemical techniques that we can use in order to reconstruct those. And so that's what you're seeing here, the reconstruction of CO2 over the past 550 million years. I wish that would... I don't know how to get that back on there. All right. In any case, the CO2 record, I'll just put it here because this one seems to be working better. The record of CO2. Let's see. That's the temperature record. That's the record of CO2 over the past. Oh no, I'm looking at the other slides. I'm sorry. Okay, so this is the oxygen isotope record, and so we talked about how oxygen isotopes are used by geochemists to reconstruct surface temperatures. And if you look at the ratio of the light oxygen 16, to the heavy oxygen 18, in carbonate minerals that were precipitated from seawater, that ratio reflects the ratio of the water that it precipitated from, so seawater in that case. And if you take carbonate remains from organisms that lived in the ocean, and you know when they lived, in this case foraminifera, and you reconstruct a timeline of oxygen isotope variation in the ocean, it looks like this over the last 8 million years. It's this black line on the bottom here. It's pretty high here, and then it sort of declines over the past, starting about 4 million years ago. Starting about 2 million years ago, we start getting these higher frequency, higher amplitude variations. Those are glacial, interglacial cycles, and the amplitude is higher because you have a larger sort of lever to pull on the ocean, the isotopic composition of the ocean, because you're actually building continental ice sheets and then letting them deglaciate and letting them grow and shrink. And so through evaporation, you're preferentially selecting the lighter oxygen 16 containing water. Then through precipitation, through rain, you're preferentially dropping the heavy oxygen containing water. And so through both processes, you're enriching the water vapor, the water that's left in the air, you're enriching it in light oxygen containing water, right? It's analogous to picking up a 16 versus an 18-pound weight, right? You'll be able to pick up the 16-pound weight more than this. The 18-pound weight requires less force, and you can carry it further. It requires less work to carry the 16-pound weight than the 18-pound weight. So we have this process, really the combination of evaporation and precipitation, that preferentially enriches water vapor in the lighter oxygen isotope as it moves towards continental interiors. That results in really light snow with respect to oxygen isotopes, snow that is highly enriched in oxygen 16 containing water. And so if that snow was to form a glacier and stay on land, not return to the ocean, then the isotopic composition of the ocean would increase over time. And so that's what you're seeing down here in this, the advance and retreat of glaciers on rapid timescales. The timescale in this case is about 100,000 years, right? And so we saw a number of these records. This one here is sea level, that have this kind of characteristic 100,000 year periodicity to them. This is sea level as related to the advance and retreat of glaciers over the last 800, 900,000 years. Similarly, let's see, I think we had one other record we looked at. Yeah, it was CO2. CO2 over that time scale has this characteristic 100,000 year period. And they've gone up and down. Why is that the case? Well, temperature's gone up and down, it's fluctuated, as demonstrated by oxygen isotopes, the oxygen isotope record. CO2 has fluctuated up and down, as demonstrated by this record, which is the CO2 concentration in gas bubbles in ice cores from glaciers. So we can sample the atmosphere going back up to almost 1 million years. We have ice that resulted from snowfall that's almost 1 million years old. Okay, so we have those two records, and we have the record of sea level rising and falling, and it matches up really nicely with those. So you can ask, what's driving these cycles? Is it temperature driving CO2? Is it changes in CO2 driving changes in temperature? Well, we know, because we've explored all of these feedbacks that connect temperature and CO2, and also the greenhouse effect, right? That CO2 really does control temperature, but temperature controls CO2 concentration in a number of ways through feedbacks. So we know they're really directly connected and indirectly connected in tons of different ways. So it's hard to say which is driving the other without understanding the processes underlying. And so we talked about kind of the last really tough concept that we tackled was Milankovitch theory, right? And so we have Milankovitch cycles where the Earth's orbit changes from being circular to more elliptical on 100,000-year timescales, this characteristic 100,000-year timescale. There are two other important pieces to this. The tilt of the Earth has a period to it. It changes. I actually have my little globe here. It changes from being about, let's see, about 21.5 degrees to about 24.5 degrees. It kind of goes back and forth like that. And it does that on a period of about 40,000 years or 41,000 years. It also has this thing called the precession, where the axis that is tilted, it wobbles. Right, it wobbles around like that. And that takes about 23,000 years. And so we have these two characteristic, or these three characteristic periods that the Earth experiences, or these cycles that the Earth experiences because of its orbit and how the orbit changes through time in these cyclical or periodic ways. And we talked about how this drives changes in climate, in temperature, really in solar insolation. It's the sort of jargony term that people use, but it changes how much energy is coming in from the sun and how it's being distributed on the Earth's surface, which we explored in detail how that drives climate. And so, when the Earth's orbit is a perfect circle, which it never is, but if it were a perfect circle, then it would be the same distance from the sun at all times throughout its orbit. The more elliptical it becomes, the further it gets from the sun during one part as compared to the other part. And so when you're in that elliptical orbit, and you're really far away from the sun, out here at the aphelion is the name of that position. If you're experiencing summertime during that position, then you're gonna have a really cold summer. Compared to the other hemisphere that would be having it here at the perihelion, which would be really hot summer. And that has really important consequence for glaciation, for keeping snow through the summertime, right? If you have cool summers, you can preserve snow and more can fall on top of it the next year. And that's how you build a glacier. So how much tilt we have is really what dictates how extreme the seasons are, right? If you had no tilt, then the sun's rays would be hitting perpendicularly at the equator all year around. But we don't, we have a tilt, and so then, the area where the sun's rays hit perpendicularly, the intertropical convergence zone, migrates throughout the year. When we're here, it's in the southern hemisphere, and then 6 months later, it's in the northern hemisphere. And so how much tilt we have modulates how extreme the seasons are. And because the axis has this precesses, it's not always summertime in the north when you're out on this side of the sun, right? Sometimes it's summertime in the northern hemisphere here. Sometimes it's summertime in the northern hemisphere here, right? Because the axis is wobbling around like this, and that takes 20-something thousand years. And so we have the combination of these three things that really work together. I had a figure that kind of showed this, right? We have these three periodic functions that kind of all combine to create this, the radiation balance between the sun, Earth, and space. And that kind of goes up and down, gets higher and lower, and it gets higher during times when we have hotter temperatures, and it's lower during times when we have colder temperatures. And now, that there indicates that it's orbital parameters, right? It's the amount of solar radiation we're getting from the sun that's driving global temperature. And that in turn is driving CO2 levels up and down. That's true, absolutely, right? CO2 levels vary in response to a whole bunch of different feedbacks. But while that is true, that temperature has been driving the climate bus for, for most, really forever, for all of Earth's history, temperature, variations in temperature are kind of driving things. They're driving things by modulating CO2 levels. CO2 is still what dictates temperature. Global surface temperature is at the mercy of CO2 levels. If you change temperature sort of artificially by increasing or decreasing the amount of energy we're getting from the sun, so increase or decrease temperature without changing CO2, then CO2 will change in response because of the feedbacks, in particular the silicate weathering feedback. If you do the opposite, right, or the other one, if you artificially increase CO2, like for instance by digging up and then burning a bunch of organic material, oil and gas, artificially, increase CO2, or increase, what I mean by artificially is increase CO2 without increasing temperature, then you're going to increase temperature, right? The two are coupled. They're coupled directly. And so, the climate records that we have look the way that they do. CO2 has varied between about 200 and about 300 ppm for the last million years. It hasn't gone out of that range. And temperature, has varied between, whatever this, this global, or this is the, I guess, the sea surface temperature, I think, for the Northeast Pacific over this time, it hasn't varied much, right? It's just kind of bounced around between those two things. But, if you go further back to a million and a half years ago, the temperature was way higher, right? And if we look at the CO2 record back there, CO2 was way higher. The two follow one another, right? And so that's sort of, where we left it. We understand how the climate works, why it functions the way that it does, why we have rain where we do, why it's the temperature that it is. We understand how the greenhouse effect works, how CO2 and water vapor primarily absorb infrared radiation and they re-emit it, right? That is warmth. That literally is temperature, right, of air. And so we understand how that works. We understand how CO2 is processed through the system. We understand where it comes from, where it goes, and we understand how the system has changed over the past few million years, and further back. If we go back, jump back to that longer record. I didn't move that slide over, but that record, for the whole of the Phanerozoic, and even back further, we have less rocks preserved as we go further back in time, but we apply the same techniques, and we have, we being hundreds and thousands of workers, spend their careers reconstructing past environmental conditions, and so we have a rich record of Earth history, and we understand it pretty well. And so with that, I'll end it, and just thank you guys again for being a part of this course, sticking around, working with me during the COVID time at the beginning, and being back on campus. And I hope you guys all have a great spring break. See you.